Okay. So today we will be studying algebra of complex numbers. So, like in the last class, we studied representation of complex numbers. Okay. So, a representation of a complex number on the Argand plane or Gaussian plane, as said, they are represented by ordered pairs of points. Ordered pairs. Okay. So 2 plus 3i and 3 plus 2i, that is 2 comma 3 and 3 comma 2, they are different points. So first, with related to algebra of complex numbers, I tell you equality of complex numbers. Equality of complex numbers. Let z1 is equals to x1 plus I times y1 and z2 is equal to x2 plus I times y2.
Sir,
And
voice is breaking, sir.
Voice is breaking. Dhananjay, for
Yes,
you.
sir.
Okay,
Yes,
just
sir.
1 minute. Okay.
Dhananjay, by mistake you on the recording, I think so.
Oh, okay. I'll just pause.
Okay, I have shared the OneNote screen. Okay, so equality of two complex numbers if z1 equal to x1 plus I y1 and z2 equal to this. And again, one condition, one hidden condition, that no funny business. No funny business means what? That x1, y1, these z1 and z2 I have given you in standard form. Standard form means what, sir? X1 and y1, they belongs to real numbers. That x1 is the real part of z1 and y1 is the imaginary part of z1. And sir, x2 and y2, they are also purely real numbers. If this condition is known, then z1 equal to z2, z1 is equal to z2 if and only if the real part of z1 should be equal to real part of z2. Real part of z1 should be equal to real part of z2, and the imaginary part of z1 should be equal to imaginary part of z2, that is y1 equal to y2. Okay, I'm giving you this purple condition in the bracket because x1 plus I y1, I'm not I want to rule out the possibility of these questions. Which question did we saw yesterday? This -3 plus 2 minus 5y times I. Such questions we rule out. From now onwards, for the rest part of the chapter, whenever I write x1 plus I y1, you should consider it to be in the standard form only. That is, x1 is real, y1 is real. x1, x2, y1, y2, they are all real numbers. So equality occurs, real part should be equal and imaginary part should be equal. Okay, so this is regarding equality of complex numbers. Then the next comes is addition of complex number. Now see, addition, now complex numbers, this is a new number system. The numbers that we had up till now, the real numbers, there the operations of addition, subtraction, multiplication, division was defined. For complex numbers, you can define the operations as you wish. As means whatever choice you have, you can define it in whatever way you want. But to define whenever you're giving a new definition, whenever you are expanding your system, what care do we take? The only care that we take is the original definition, our original properties should also be satisfied. That is our only target. Like when we studied trigonometric functions, we expanded our definition for second quadrant, third quadrant, and the fourth quadrant. But how, in what way did we give the definition? That the sine and cos for the acute angles that we studied, the origin of trigonometry for the acute angles, where they violated, no, we did not change the definition, we simply expanded it. So that way, addition of complex numbers, whatever definition we will be giving, we just have to make sure that a new definition, it is completely to our free will. We can define, we have complete freedom. We can define it as however we like, but we will take just a certain care that our original condition of the real numbers, that the such this property holds true in the set of real numbers as well. Our original condition of addition do not get violated. So z1 plus z2 is defined as, if two numbers are there, x1 addition y1, and another number is x2 addition y2. No need to say x1, x2, y1, y2 are all of them are reals. Okay, and you're just simply adding two complex numbers. So add them part-wise. Part-wise means add the real parts together, add the imaginary parts together. The real parts will be added together, the imaginary parts will be added together. That's it. Okay. So now, if this is the definition of z1 plus z2, I hope there is nothing complicated in saying that, sir, since z1 plus z2 means we know that since x1 plus x2 is equal to x2 plus x1, and similarly also, sir, y1 plus y2 is equals to y2 plus y1. So can I say that, sir, z1 plus z2 is equals to z2 plus z1? I don't think it's very anything hard to say. This property is called as what? Associative, no, commutative property. Whatever order you take, it doesn't matter in terms of addition. Another thing, in real numbers, x1, x2, xy, x1, x2, y1, y2 are all real numbers. So in set of real numbers, we know that x1 plus x2 plus x3, this bracket, and if you add x1 plus x2 first, and the result you add it to x3, this is same. In set of real numbers, this is satisfied. Similarly for y1 also, y1, y2, y3. So if I write z1, add the result, add z1 to the addition of z2 and z3. And the another is, sir, first I will add z1 and z2, and the answer that I get, that I will add it to z3. Will these two complex numbers be equal? Yes or no? Pujita, Dhananjay, Afrin. Do you agree with me that these
Yes,
properties?
Yes, sir.
These are trivial properties now, since the x1 plus x2 for x's, take x's and y's, imagine that how they are satisfying in real numbers. Similar properties will be satisfied in complex numbers also. This property is called as associative property. So closure property. Closure property is what? So take any x1, x2 reals, any x1, x2, the addition also belongs to real only. If any two real numbers you take, their addition belongs to real. Any two y's you take, their addition belongs to real. So sir, take any two complex numbers. They will have some real x1, x2, y1, y2. So their addition will also belongs to the set of complex numbers only. If you agree, then this property is called as closure property. That from the bag of complex numbers, you pick up any two elements add them, the answer that you get will be in that bag only. You do not have to search somewhere else. Like in the set of natural numbers, and if I give the addition of the operation of subtraction, it is not a closure property. It does not satisfy closure property. Take any two numbers from the bag of natural numbers, do subtraction, the answer will be in the bag. This is a false statement because that closure property is not satisfied. So addition, the complex numbers, addition also satisfies the closure property. Additive identity.
Sir, additive identity is Z equals to minus Z.
Z equals to
Minus Z, no sir.
no. Additive identity is what, always remember, what you're talking about is additive inverse. Okay, additive
Okay,
identity and additive inverse. So I will not give you the I will not write the complete sentence definition of these two. These are very trivial terms. Now we have already studied it for in the set of real numbers. Identity for identity with respect to addition. Roughly speaking, identity with respect to addition. So a number in the bag of complex numbers, find a number when added to Z. Let's say Z plus what should I add? Or let's say that number in the opposite direction also, if I add. This number should give me Z only. Now, whatever this answer is, whatever number you will find, if you can find some number such, that red question mark will be my additive identity. Identity means what? The identification of Z does not changes. Z, when you add to that red question mark, it remains Z only. The red question mark, when added to Z, it remains Z only. So by observation, I think you can see that, sir, additive identity is equals to 0 plus I times 0 is equals to additive identity. And remember, additive identity is not of a particular complex number. Identity is of the set of complex numbers. The complete complex number C set with respect to addition, there is a special complex number that is 0 plus I0. Now, additive inverse. Now, what is additive inverse? Sir, additive inverse is that number with respect to Z1. Now, I will give you some Z1. With respect to Z1, find some number which, when added to that number, the answer should be what? The answer should be additive identity. For multiplication also we do multiplicative identity. Multiplicative identity, what will be the answer? Z multiplied by some number is equals to some number multiplied by Z should be equal to Z only. And what will be multiplicative inverse? Z1 multiplied by some number should give me the multiplicative identity.
So multiplicative inverse is 1 by Z.
Yeah. Now 1 by Z is the symbol of that multiplicative identity, and this additive inverse. Now, okay. So 1 minute, I will come to that point. 1 by Z. Additive identity. Now I will have to represent, I will have to find some number. So first of all, Z1 plus this box. Can you find some number that will give me the answer? What is my additive identity? So my additive identity is 0 plus I times 0. This we have already found. This we have already defined, that 0 plus I times 0 is my identity of the set of complex numbers. So now if my Z1 is equals to, z1 is equals to x1 plus I times y1. So by observation, you can see that, sir, if z x1 plus I times y1, I want to add some number so that my final answer is 0 plus I times 0. So by observation, can you see that, sir? How do we do this addition? ये यहाँ पे जो addition है, the addition that is the addition of the complex numbers, the bold addition. How do we do that? So we add part by part, real part to real part, imaginary part to imaginary parts. This x1 should be x1 plus something should give me 0. So the answer should be, sir, here the answer is minus of x1, because x1 addition minus x1 is 0. y1 addition minus y1. That will give me 0 times, that will give me the second 0. Okay, so my answer is minus x1 plus I times minus y1. Okay, so this additive inverse is of, now see, additive identity was of the set complex numbers, but additive inverse is of the particular complex numbers. We say that additive inverse of x1 plus I times y1 of this particular complex number, the additive inverse is minus x1 plus I times minus 1 minus y1, that is minus x1 minus I times y1, one and the same thing. So with respect to other, for a particular all the complex numbers, each and every complex number has the same additive identity because it is of a set, but different complex numbers have different inverses. And now you must be thinking, sir, this is the minus z. Now minus z is a symbol. Additive inverse of x1 plus I by 1 is this, represented by symbol minus z or minus z1. Okay, so whenever you encounter this symbol minus z1, so you should, what actually I'm asking you is, minus z1 means it is additive. What is the additive inverse of z1? The meaning of this statement is, what is the additive inverse of z1? Afterwards, after some time, we will prove that, sir, ये जो minus z1 है, this minus z1 is actually minus 1 into z1. This can be proved later on, nothing difficult, because right now we do not know what is this multiplication operation. In the set of complex numbers, we do not know how to multiply different complex numbers. So z1 is a complex, minus 1 is also a complex. How to multiply two complex numbers right now we don't. Okay. So understood the meaning of additive inverse. Inverse is with respect to a particular complex. Identity is with respect to the whole set. Now subtraction of complex numbers. This was the second operation, I think so. Addition. Subtraction of complex numbers, again z1 plus z2. Now z1 is given, z2 is given. Z1 subtraction z2. Now z1 and z2, you know that, and you have to find this subtraction operation. Okay. Subtraction for z1 and z2, this is defined to be equals to what? So z1 is there, first number is there, let it be as it is. The second complex number that you have, so you can definitely find the additive inverse of the second complex number. Okay, now whatever is the additive inverse of the second complex number, you just add it to the first, and this addition operation is well defined. Addition we know up till now. So this is the definition only of the subtraction of complex numbers. To subtract means to add the additive inverse. Got it? To subtract Z2 from Z1, just add additive inverse of Z2 to Z1. So if this definition is given, so Z1 is equals to x1 plus I times y1, Z2 is equal to x2 plus I times y2, and Z1 minus Z2 will be equal to x1 plus I times y1. This subtraction, which I don't know what it is, and the second operation, the second complex number is x2 plus I times y2. This is equals to x1 plus I times y1. Addition, what to add? The additive inverse of the second complex number, and the additive inverse of the second complex number I know. What is the additive inverse of x2 plus I y2? Whether it is minus x2 minus I times y2, yes or no, that we have seen previously. Additive inverse of x1 plus I y1 is negative x1 plus negative I y2. This we have seen now.
Yes, sir.
And how do you perform addition? Sir, I perform the addition by taking part-wise. Part-wise, I will just do so x1 plus of minus x2, and now this is just similar to real numbers. In real numbers, we know what is this thing, and then plus I times y1 plus of minus y2. And in set of real numbers, we know that x1 plus of minus x2 is the same as x1 minus x2. So this also you can remember. So just definition wise, understand that this is x1 minus x2 plus I times y1 minus y2. The actual definition was this: add the additive and add the opposite number. From that we derived that if you directly subtract also part-wise, it's one and the same thing. Part-wise subtraction also if we do, it's one and the same thing. This is the proof. Okay. Now if you can get this, so in set of real numbers, we know that from the set of real numbers, we know that if you pick up any two real numbers, x1 and x2, any two real numbers, and if you do the subtraction, the answer belongs to real only. If you pick up any two real numbers, y1 and y2, and if you perform the subtraction, the answer belongs to real numbers only. So can I say that's a z1 subtraction of x1 and subtraction of the complex numbers? Satisfies closure property, because whatever z1 and z2 you pick, any random number of your choice, their subtraction will always belongs to the set of complex numbers, no matter what z1 and z2 you choose. Okay. If you, sir, if I choose z1 equal to z2, so then z1 minus z2 will be 0. So 0 is a real number. Keep in mind all real numbers are complex numbers. Okay, subtraction satisfies closure property. Now associative z1 minus z2 minus z3. What is this, sir? First perform this subtraction z2 minus z3, and whatever answer you get, do that subtraction from z1. And another person says, sir, first I will perform z1 minus z2, and from this answer first I will calculate, after that I will do minus z3. So you can see that these two are not equal. Just verify it yourself. How to verify? Because sir, x in the set of real numbers, it's easy to verify that x1 minus x2 minus x3 and x1 minus x2 bracket minus x3. So these are not one and the same thing. So associative property does not satisfy. Okay. Does not satisfy associative property. And also z1 minus z2 is not equal to z2 minus z1. Not commutative. I hope I can skip the explanation of this part. Neither it is commutative nor it is associative. The only thing that is satisfied is closure.
Yes, sir.
Okay. This is with respect to subtraction. Now multiplication of complex numbers. Multiplication of complex numbers. Now this is a little bit tricky business. Z1 is equals to x1 plus I times y1 and z2 is equals to x2 plus I times y2. So z1 into z2 is equal to. Now you may define it whatever way you like. I have already told you, for whenever you're defining a new concept, you can define multiplication division in whatever way you want. So you could have defined it. Let's say takes a one number is x1 plus iy1, x1 plus iy1, and the other number is x2 plus I times y2. So easiest definition would be what? So define the multiplication as x1 multiplied by x2 plus I times y1 multiplied by y2. This could have been the definition, plus I times y1 multiplied by y2. So life would have been easy. x1 x2 y1 y2 khatam. Real part to real part multiplication, imaginary part. But this was not the definition given by the mathematicians who developed the theory of complex numbers. Why did not they give this definition? Because they wanted the properties that were holding true for set in the set of real numbers. Those properties should not get violated in the set of complex numbers, because ultimately all reals are complex. So now in the set of real numbers, if you had, suppose hypothetically, in the set of real numbers, if you have a plus b multiplied by c plus d, how do you do it? So I multiply ac also, I multiply bd also, this vertical. After that I also do ad and I also do bc, and this all these terms I take the addition, distributive, a simple binomial into binomial multiplication and nothing else. So since in the reals I multiplied in this way, why not multiply in the same manner in the set of complex numbers also? And whatever that answer will be, I will give that as my definition. So I will define my multiplication in such a way so that my target, my original target is that the distributive law is satisfied. So if at all, assuming that since in order to fulfill my original target of satisfying the distributive law, in order for distributive law to be satisfied, what would have been the answer? So the answer in that case would have been, sir, x1 multiplied by x2 plus I square y1 multiplied by y2. After that, sir, there would also have been a term of I times x1 y2, and sir, there would also have been a term of I times x2 y1. So I will give this to be my definition. Yeah, I know it's a very big definition, but after this basic definition, though it is a complicated, but afterwards, since our original target of distributive law and all are satisfied, we do not have to study any new properties with respect to complex numbers. Whatever thing that we have studied for reals, the similar analogy we can do in complex also. So my definition, I will give it to be equal to x1, x2. This I square y1, y2. I square is actually -1 only. So minus y1, y2. Yes or no? I square is -1 only. This I square is actually -1. X1, x2 minus y1, y2 is the real number, is the real part, because x1, x2, y1, y2 are all real numbers. And imaginary part is what? The coefficient of I. The coefficient of I is, sir, I times x1, y2 plus x2, y1. This I gave as my definition. Okay. This is my definition of the multiplication of complex numbers. So if any book, if you refer with respect to complex numbers, they will give you that's a definition of complex numbers is something like this. Definition of Z1, Z2 is real part of Z1 multiplied by real part of Z2 addition I times real part of Z1 multiplied by imaginary part of Z2 plus real part of Z2 multiplied by imaginary part of Z1. This is the definition. But so do we need to remember this definition? You do not need to remember this definition, because what I have told you, this ugly looking definition, this complicated definition, why was it given? With the intention of satisfying distributive law. So if this definition was given with the intention of satisfying distributive law, so during the exam, if I just ask you multiply two complex numbers, so don't rectify this definition, don't memorize this definition. On the paper only, just do the cross multiplication of binomials as you do. Okay, will that be okay? So if that is clear, so just do some multiplications. Solve, multiply. First, 2 plus 3i multiplied by 4 plus 5i. Second, five minus 2i plus 4i. Don't bother to write the answers in the chat box. Just tell me 1D, 2D, 3D, 4D, and so on. Okay. As you go on solving, just write 1D, 2D, 3D in the chat box. That will be sufficient. Let's see. Okay. For initial practice, you can say, you can form the habit of 2 plus 3i, 4 plus 5y, and I will multiply it using distributive law. Again, when I'm telling you that, sir, I will multiply it using distributive law, actually I'm telling you an incorrect statement, because I do not know whether complex number satisfies the property of distributive law or not. But this definition, this basic definition was given with the target of with that original target of the distributive law over binomial being satisfied. So I will not memorize this red bracket definition. I will memorize this. I simply know how to multiply binomial by binomial, and I will apply my knowledge of binomial and algebraic expressions that I know. So here that will be 4 2s are 8, 5 3s are 15, but this 5 3s are 15 will be with a negative sign, because 15 I square is negative 15. After that, cross multiply, 5 2s are 10i, and here it will be 12i. Addition. So the final answer is equals to negative 7 plus 22i. Okay. Second one, 5 minus 2i, 3 plus 4i. In the board exam, do not do this cross multiplication. Just 1 second, students. 1 minute. Yes. 5 minus 2i, 3 plus 4i. So it will be 5 3s are 15. This will be minus 8 and I square. Minus 8 and I square, it will change the sign. Okay. And then it will be 20i, and this will be minus 6i. So this will be 15 plus 8 is 23. Yes, correct. And 23 plus 14 times I. Third one. Now third one I will directly do without writing it in the vertical format. Minus 8. This is minus 8 and the second multiplication. This is minus 8 and this is minus 3. But minus 3 I will always have to change sign. Whenever we are multiplying I and I, change the sign. So this is minus 8 and plus 3. Minus 8 and plus 3 will give me the real part. The real part will be minus 5. And for the imaginary part, no need to bother about the signs. Just multiply alternately. Minus 2 will be multiplied by 1. That is negative 2 only. and minus 3 will be multiplied by 4, that is negative 12 only. Negative 12 and negative 2, that is negative 14 times I. Okay. Five plus 2i, 5 minus 2i. So this will be 5 plus 2i, 5 minus 2i. Can you see that this will be equals to 5 square, so 5 square, and this 2i and minus 2i, when I will multiply this way, it will be minus 2i whole square. And this cross multiplication, 5 into negative 2i, 5 into positive 2i, that will definitely get cancelled. So my final answer is 5 square minus 2 square and I square. So I square will make this plus. So can I say that, sir, my final answer will be equal to 5 square plus 2 square? Okay. Why I'm writing the answer in this format, that I will tell you afterwards. This question has something to do with conjugate. So I will just write this answer is equals to 29. Fifth also, 7 plus 3i, 7 minus 3i. Can I directly say that? So the answer will be 7 square negative 3i whole square. Negative 3i whole square means actually plus 3 square. So this will be equals to how much? 958. The last one is 8 square minus 59 whole square. Minus 59 complete square is equals to addition 15 square. So this will be 18, 15, 17 triplet. 18, 15, 17 triplet. So it will be 17 square. This is 2. Got it? Multiplication. Yes or no? The simple multiplication process. And now if you know this multiplication, if you're comfortable with the multiplication, how to multiply any two complex numbers. So now if I tell you, once again, yes, that since we already know, sir, the x1 y1 closure property, take any two complex numbers z1 multiplied by z2, the answer will always belongs to the set of complex numbers only. Why? So because x1 x2 x2 y1 y2, these are all my real numbers. I can definitely say, sir, that x1, whatever combination you are doing, that x1 x2 minus y1 y2, the real part of the product real part, this is a real number, and the product is z1 z2, the imaginary part of the product, is x1 y2 and x2 y1 addition. This is also again a real number. So z1 and z2, pick up any two complex, their product will be a complex number. Second, commutative property. So what is z1 multiplied by z2? z1 multiplied by z2 is x1 x2 minus y1 y2 plus I times x1 y2 plus x2 y1. And what is z2 z1? Just instead of x1 I will have to write x2. x2 x1 minus y2 y1 plus I times, instead of x1 y2, first term will be x2 y1 and the second term will be x1 y2. I've written, means in the z2 z1 I've written this first number over x2 plus I times y2 and the second number downward, x1 plus I times y1, I have multiplied. Can you see that? So this x1, x2 is same as x2, x1. This y1, y2 is same as y2, y1. So the subtraction will be same. x1, y2, x1, y2, x2, y1, x2, y1. The addition is commutative in real, so this is one and the same thing. So z1, z2 is equals to z2, z1. Commutative property is satisfied. Okay. Associative, I leave it to you. Associative, you have to do a very long calculation. It is just a verification, nothing more. Is equal to z1, z2 multiplied by z3. This I leave it to you, verify yourself. This verification will go little bit long because z1, z2 multiplication only you see with the real part that you're getting is such a big real part. x1, x2 minus y1, y2. Such a big imaginary part. And this multiplication with x3 plus I times y3. You can do the multiplication, is not at all difficult, but I just don't want to waste the class time in the simple arithmetic. It's just simple algebraic calculation of algebraic expressions and nothing more. Associative, you can verify yourself. So closure is satisfied, commutative satisfied, and associative is also satisfied. Now coming to multiplicative identity and multiplicative inverse. So multiplicative identity, multiplicative identity, whenever we talk of identity, the identity with respect to multiplication operation, identity is always defined with respect to what? Identity is always defined of a complete set. Multiplicative identity of the set of complex numbers. Of the set complex numbers. So how to define this multiplicative identity? For a given complex number z, you have to find some complex number which when multiplied in the commutative order also z multiplied by box or box multiplied by z. Okay, the answer should be find such a complex number so that the answer should be z itself. Whatever complex number you pick, that it should be the answer should, on multiplying by the red question mark, it should give me the same complex number which you have picked up. So if my original complex number is x1 plus I y1, some complex number you picked up, and you have to find a complex number, the infinite complex numbers that you have to find some complex number which should give me the same answer, x1 plus I y1. So which is that complex number? Just by observation, I think it is nothing difficult to observe that, sir. If you take that, a general feeling is, sir, give a trial and error. If we do, so try by 1 plus I times 0. Try what happens with after multiplication. x1 multiplied by 1 will be x1. I times y1 multiplied by 0 will be x1, 0 only. So the real part is x1. And what will be the imaginary part? The imaginary parts of this x1 will multiply by 0, so it becomes 0, and y1 will multiply by I, the answer will be y1. Okay, so the answer is x. The additive multiplicative identity is 1 plus I0. Just 1 second, students. Okay, sorry for the disturbance. So x1 plus I y1, and it should be multiplied by 1 plus I times 0. You can check that this complex number that I have written in purple, this is actually the multiplicative identity. With whatever number you multiply, it will give me the same number. So multiplicative identity of the set of complex numbers is 1 plus I times 0. This is equals to 1 plus I times 0. It is of the whole set, not with respect to a particular complex number. Now multiplicative inverse. Multiplicative inverse of a complex number, of a particular complex number, of a complex number. Identity is with respect to the whole set. Each and every complex has the same identity. Identity is of the complete set. Inverse is of a particular complex number. Of a complex number, let's say Z1. Okay. So how to find what is the definition of multiplicative inverse? The definition of inverse is only that, so with respect to multiplication you are defining, no? With respect to multiplication, so Z1 multiplied by, find a suitable complex number. Find a suitable complex number which when multiplied by the number that you picked up, the answer should be multiplicative identity. The operation that you're performing, its inverse you're taking, inverse with respect to multiplication. So the answer should be identity with respect to multiplication. And so what is my identity with respect to multiplication? My identity with respect to multiplication is 1 plus I times 0. My identity with respect to multiplication is 1 plus I times 0. So Z1 multiplied by some box should be equals to 1 plus I times 0. So it's a convenience that Z1 multiplied by box is equals to 1 plus I times 0. So it's a convenience to say that this box, whatever number you will find out, let it be represented by a symbol. The symbol of this box is symbol of the multiplicative inverse is, so on the RHS is 1, so let it be represented by the symbol 1 upon Z1. Now don't think right now that you know the division 1 divided by Z1. This is not division. 1 upon Z1 is not division of 1 divided by Z1. It is just a symbol 1 horizontal line Z1. So now what is this? Now what is the value of this 1 horizontal line Z1? So if Z1 is equals to X1 plus I times Y1, then 1 upon Z1 is equal to, now assume means for next 3 or 4 minutes, just consider that maybe that God appeared in my dream and he told me that the answer is X upon X square plus Y square. Sorry. Yeah, okay. Let it be this X and X plus IY only. So 1 upon Z is X upon X square plus Y square is the real part of this complex number, and the imaginary part of this complex number is minus Y upon X square plus Y square. So how do you know this? For next 3 or 4 minutes, just accept that something came in my dream and I know this answer. If Z is given to you, the real part of Z and the imaginary part of Z1, then the inverse, multiplicative inverse, 1 horizontal line Z1. I'm not saying it is 1 divided by Z1. I'm saying the multiplicative inverse, 1 horizontal line Z1, it will be X upon this. Now here it is X upon X square plus Y square, the real part, and the imaginary part minus Y upon X square plus Y square. Verify this yourself. Do it right now. What I'm telling you, the question is verify whether it is really 2. X plus IY, this number, and the other number is what? x upon x square plus y square minus I times y upon x square plus y square. Whether this multiplication is actually equal to 1. Verify. This is your question. Right now, do it. So how to do? You know how to multiply two complex numbers. We have done these questions. Here I gave you numerical values. Here I have gave you, instead of numerical values, I have gave you an algebraic expressions. Use your knowledge of algebraic expressions, multiply. If you are able to do, if your answer is verified, tell me in the chat box. Yes, sir, done. One horizontal line z or 1 upon z is the symbol, and this is the value of that. Multiplying 10. Dhananjay Pujita, is it over?
No, sir.
No, sir.
Okay. Pujita, how did we do the earlier multiplication, sir? With 2 plus 3i, 4 plus 5i, we just wrote in the vertical format. If you should get comfortable with the horizontal multiplication, because in competitive you don't have the time to first horizontal to I will write in the vertical direction and then I will multiply. You should get comfortable with horizontal only. But if for the starting purpose, okay, this is our first lecture for multiplication. So we write in the vertical direction, z1 below z2, and then we multiply using the same distributive law. Though it is not correct, but we still applied how the multiplication was defined. 4 2s are 5 3s are 15, and 15 with the negative sign, and the cross 2 into 5, 4 into 3. Okay, so here also I will do that only. So my one number is x plus I times y. My another number is, sir, x upon x square plus y square. This is the real part, and the imaginary part is minus y upon x square plus y square. The imaginary part is not minus I times, okay? Minus y upon x square plus y square. Imaginary part is also real number only, keep in mind. And I have to multiply these two. Just check whether they are actually equal to 1. I don't know whether what the answer will be. I'm just multiplying. So for the real part of the product, what I will do, I do not want the value, I do not want anything related to I. So I will just multiply these two. These two real will give me the answer as a real number. These two i's I will cancel out, means will product will be I square and then the answer will be -1. So the real part of the product is what, sir? X multiplied by x upon x square plus y square. So is it x square upon x square plus y square? Yes or no? And from the right hand, this side, I into I, this is minus y square upon x square plus y square, but I square is also there, minus I square this. So whenever I have told you that change the signature, so this minus will become plus. After this, what? Plus I times, what is the other part? The other part is, now do this cross multiplication. For cross multiplication, these two and these two. So x into this will be negative xy upon x square plus y square. And here it will be positive xy upon x square plus y square. So is the answer equal to, this addition is 1, yes or no? Plus I times 0. Done. What you were doing with numerical numbers, the numericals, the same operation I gave you with the algebraic expressions. Instead of 1 2 3 4 5 6 initially, and now here I gave you in terms of x and y. Is it clear, Dhananjay, Pujita, Nitin?
Yes, sir.
Hence, verified. Okay. So this is the verification. This is not the proof that what we have told. This is not the proof that this answer is the inverse. This is just a verification. I just gave you, I did not explain you, I just gave you that this is the inverse, and you verified. Okay, sir told us, so let's verify. And yes, what sir has told, it is right. Now, sir, do we need to memorize this such a ugly formula? You don't need to memorize this ugly formula. How to find the answer? There is a trick to memorize this thing, to understand this thing. See, 1 upon z1, the symbolically, I've already told you this 1 upon z1 is a symbol. This 1 upon z1 is 1 upon x plus iy. This is just a symbol and nothing more than that. In fact, to tell it 1 upon z is also partially incorrect. One horizontal line z1, or in daily language we can call it 1 upon z1. 1 upon this. Okay, because up till now we do not know what is upon, because up till now upon means division. Up till now we have not defined division. So rather than memorizing this thing, how to understand means how to, is there a trick to understand it? So I will just tell you the trick. The trick is, see, roughly multiplicative inverse of z1. Symbolically it is 1 horizontal line z1, 1 horizontal line x plus iy. Okay, so now I will just do, now what I'm going to do ahead is just death of mathematics, but for understanding, let's do it. I will just multiply it by x minus iy upon x minus iy, even though I do not know what is the meaning of division. Even though division is not defined, but still I'm doing it. X minus iy upon x minus iy, considering that this purple number is as 1. That is completely wrong, but let's do it. X minus iy. So what will remain in the denominator? X plus iy and x minus iy. And now this is easy. The numerator will be, sir, x minus iy, and the denominator, can you calculate? X plus iy multiplied by x minus iy. Something that I gave you a questions earlier. 5 plus 2y, 5 minus 2y. Is it 5 square plus 2 square? 7 plus 3y, 7 minus 3y. Is it 7 square plus 3 square? 8 plus 59, 8 minus 59. Is it 8 square plus 15 square? x plus iy, x minus iy. So x into x will be x square minus.
Sir, here x minus I we can cancel out now, sir. Then we will get 1 by x plus iy.
Yes, you will get 1 by x plus iy. So that only what we want to calculate, na?
Sir.
That is our original target.
Yes.
Okay, means you are starting here, then you're cancelling it, you will again reach here only. Move forward. So you are again rewinding to the first step if you cancel it out. Yes or no? So this is x
Yes,
minus
sir.
iy numerator, and then the denominator, this multiplication will be what? Then denominator multiplication will be x square minus iy complete square. Iy complete square will be, here change the signature, x square plus y square. Okay. So now x minus iy upon this is a real number. So the denominator is a real number. So you can separate it x upon the denominator, that is x square plus y square. The remaining minus iy upon the denominator, that is x square plus y square. So this way you can remember how to find the inverse of a particular number. 1 by z1, which was actually symbolically, which was 1 upon x plus iy. This whole process is just death of mathematics, but I'm just doing it. That is helping me to remember that this x upon x square plus y square minus iy upon x square plus y square. And yes, so this is the multiplicative inverse of z1. My purpose is solved. Okay. So now do you understand how to remember it? Instead of memorizing this ugly formula,
Yes,
in the
sir.
exam, on time also you can calculate the inverse of a particular, multiplicative inverse of any particular given number. Okay.
Yes, sir.
Okay. So evaluate first. Multiplicative inverse of multiplicative inverse mi of 2 plus 3i. Second, multiplicative inverse of
Sir, first answer is 2 by 13 minus I into 3 by 13.
correct.
Sir, second answer is 3 by 25 minus I into 4 by 25.
Yes, correct.
Sir, one scroll up, sir, for third question.
Multiplicative inverse of 3 minus 4.
Sir, third answer is 3 by 25 plus I into 4 by 25, sir.
No. Three by 25 plus.
I into 4 by 25, sir.
No, read the question correctly. It's not a printing mistake, okay? What I have written is not a printing mistake. Read it correctly. Multiplicative inverse of 3 minus 4. So just for the completion purpose, I'll tell you the first one, multiplicative inverse of 2 plus 3i. Method 1, memory of formula. Formula memorized. The formula memorized, or let's say definition to memorize. The formula of the multiplicative inverse is memorized. So if you tell me 2 plus 3 and multiplicative inverse, the symbol is 1 upon 2 plus 3i, and here this is equals to 2 upon 2 square plus 3 square minus I times 3 upon 2 square plus 3 square. So the sir answer would be 2 upon 13 minus I times 3 upon 13. This is one way, memorize it, or the other way would be, which is actually the wrong way, but still we are interested in the answer. That helps us to find the answer. Method 2. Wrong method, but gives us the answer, but helps to find the answer. What is this method? So 1 upon 2 plus 3i is equal to 1 upon 2 plus 3i multiplied by 2 minus, there's something similar to rationalization of surds. Here it is not called as rationalization, something similar to that. So 2 minus 3i upon, it will be 2 square plus 3 square denominator. So it will be 2 upon 13 minus I times 3 upon 13, which will be the answer. Okay. The second question also same, multiplicative inverse. Symbol of multiplicative inverse of 3 plus 4i. 1 upon 3 plus 4. And this is the, I will directly write the final answer. You know how to find it. It will be 3 upon 3 square plus 4 square, that is 25. 3 square plus 4 square minus I times 4 upon 3 square plus 4 square. So this will be equal to 3 upon 25 minus I times 4 upon 20. Dhananjay, I hope this was correct. First two.
Sir, third answer I'm getting 3 by 25 plus I into 4 by 25 only, sir.
You have to, what you have calculated, Pujita, is multiplicative inverse of this.
Yes,
You
sir.
You have to calculate that answer. It's again multiplicative inverse you have to calculate. No?
Okay, sir. Okay, sir. Okay.
Dhananjay did the easy job. 1 upon 2 plus 3i, 1 upon 3 plus 4i. That is not how you have to write it. This should be the answer. Let z is equals to 3 minus 4i. Multiplicative inverse of z represented by 1 by z is given by 1 upon, symbolically it is 1 horizontal line 3 minus 4, right?
Sir,
And the answer of this is, just 1 second,
sir, I
Pujita.
got one right.
This is, will be 3 upon 3 square plus 4 square addition I times 4 upon 3 square plus 4 square. So this 1 by z is actually equal to 3 upon 25 plus I times 4 upon 25. This is multiplicative inverse of z. Yes, tell me your doubt, Pujita.
Sir, I'm getting after this multiplicative inverse of multiplicative inverse now, sir.
Yes, correct.
So 25 by 75 minus I into 25 by 100 I'm getting. Sir, we have to cancel it out.
25 by 75
minus I into 25 by 100.
No.
Sir, I'm
Cancel it,
getting the same answer again, sir. 3 minus
Yes, 3
4i.
minus 4i only you should get. And the answer will be 3 minus 4i only. Purita, maybe you did some calculation mistake. Let's see.
I multiplied with
See.
25. Sir.
Okay, see this 1 by z equal to this much. Multiplicative inverse of z. The purple thing here, the multiplicative inverse of this much. This is the purple here. Now you have to find again the multiplicative inverse. Multiplicative inverse of this purple thing is what? So the purple thing is 1 by z. So you have to find multiplicative inverse of 1 upon z. 1 upon z is some complex number. So how you represent it? Multiplicative inverse of 1 upon complex number, this complex number, it is represented by 1 horizontal line 1 by z. Yes or no? Representation is correct, Pujita?
Yes, sir. Yes, sir.
1 horizontal line 1 by z. Now what is this equals to? This is equals to 1 horizontal line, and this was actually 3 upon 25 plus I times 4 upon 25. Now comparing it with x plus iy. Now my x is equals to 3 by 25, my y is equals to 4 by 25. So little help of the formula I can take, or you can write here multiplied by 3 by 25 minus I times 4 by 25 upon 3 by 25 minus I times 4 by 25. So in the numerator will be simply 3 by 25 minus I times 4 by 25. This completely divided by the denominator, and my denominator is something of the form x plus iy, x minus iy, and this will be given by 3 by 25 complete square plus 4 by 25 complete square. Yes or no, Pujita?
Yes, sir.
So here the answer will be, so 3 by 25 minus I times 4 by 25. Now denominator, don't think so I will take the actual squares. It is something 3 square upon 25 whole square, 4 square upon 25 whole square. So now here just concentrate on this denominator. This denominator is same only, so that can be written as it is 25 square. And here the numerator will be 3 square plus 4 square. Correct?
Yes, sir.
So the numerator 3 by 25 minus I times 4 by 25 complete divided by 3 square plus 4 square is 5 square. So you can call it as 25 only. And here the denominator is 25, so denominator of the denominator. Okay, it's 25, it's 25 square. So cancellation wise, this will be 25 will get cancelled and this square will get cancelled. Correct?
Yes, sir.
And this particular denominator, it is 1 upon 25. So this complex number divided by a real number, 1 upon 25. So do I get it equal to 25? This will, while going up, it will get 25 multiplied by 3 by 25 minus I times 4 by 25. This 1 upon 25, when it goes up, it will become 25 into. Getting, Pujita?
Yes, sir.
Okay. So this will be what, 25 into this is now just simply 25 into 3. This will be 3 minus I times 4. That's it. So the moral of the story is multiplicative inverse of 1 by z. Symbolic, it is 1 upon 1 by z. So 1 upon 1 by z. What was my z? Z was my 3 minus 4i only, no? This was only my z. So this was only my z. Z equal to 3 minus 4i. When you take inverse, multiplicative inverse, you will get something really different number. But when you again take the inverse, you will get the same number. Okay.
Yes, sir.
So 3 minus 4i is z. This is one complex number z1. And my another complex number is 3 upon 25 minus, 3.25 plus I times 4 upon 25. This is my z2. Multiplicative inverse of z1 is z2. And multiplicative inverse of z2 con, it is z1. Something in set of something similar to that of real numbers. The reciprocal of 2 is 1 by 2. The reciprocal of 1 by 2 is 2. The reciprocal of 7 is 1 by 7. The reciprocal of 1 by 7 is 7. Okay. This is with respect to multiplicative inverse. More questions about multiplication we will do tomorrow. Not tomorrow, next lecture.